In 1959, a train line ran straight through the middle of the Tengger Desert in northern China. Within weeks of opening, it was buried, not damaged, buried. Sand had swallowed entire sections of track, and crews had to dig it out by hand with shovels, only to watch the wind bury it again a few days later. 60 years later, that same stretch of desert is green, not a small patch, not a demonstration garden for cameras. Thousands of square miles of what used to be moving sand now grows wheat, rice, corn, melons, and fruit trees. Farmers who were told the land was dead are pulling harvests out of ground that used to be nothing but dunes. This is one of the largest land transformation projects in human history, and most of the world barely knows it happened. It involved straw, salt water, dead trees, robots, and a scientist who spent 30 years being laughed at. If you enjoy videos like this one, hit the like button and subscribe, because these take a long time to research and put together. But before we get to the green fields, you need to understand just how bad the problem was. Because China was not fighting a patch of dry ground. China was losing an entire country to sand, one field at a time. Picture a farming village in Inner Mongolia in the early 1990s. A family has worked the same land for 4 generations. The soil is thin, but it works. They grow enough to eat, enough to sell, enough to keep going. Then one spring, the wind comes in from the northwest carrying sand. Not a dust cloud, a wall of it, hundreds of feet high, moving fast enough to strip paint off a truck. When it passes, there is sand piled against the north wall of every house, sand in the well, sand in the wheat. The family sweeps it out and plants again. The next year, more sand. The year after that, the dune at the edge of the village has moved 50 feet closer to the houses. Sand dunes move. That is the part most people do not understand. A dune is not a hill. It is a slow wave. Wind picks up grains from one side, carries them over the top, and drops them on the other side. Do that for a year, and the entire dune has crawled forward. In some parts of northern China, dunes were advancing more than 60 feet every single year, fast enough that a person could stand in a field and know that within their lifetime, that field would be gone. By the 1990s, China was losing an area of usable land roughly the size of Rhode Island every single year to desertification. Villages were being abandoned. In some counties, families packed everything they owned onto carts and left because there was simply nothing left to farm. Government surveys found entire settlements where the sand had reached the rooftops. There are records from that period of school teachers in Gansu describing classrooms where they had to shovel sand off the desks before lessons could start. Wells that had served a village for a century filled in over 2 or 3 seasons. Roads disappeared entirely, so trucks stopped coming, so the shops closed, so the young people left, so there was nobody left to dig out the wells. Desertification rarely kills a village directly. It just removes one thing at a time, until staying stops making sense. And the sand did not stay in the countryside. Every spring, dust storms rolled south and east and hit Beijing. The sky would turn orange. Flights got canceled. Hospitals filled up with people struggling to breathe. Cars parked on the street would be covered in a fine yellow film by morning. The dust traveled so far that it landed in Korea, in Japan, and in some cases, was detected drifting all the way across the Pacific to the west coast of the United States. So, this was not a rural problem that could be ignored. It was arriving in the capital city, in the lungs of 20 million people, every single spring. Now, here is the part that made it so difficult. China has a math problem that almost no other country has. It holds around 20% of the world's population. It holds around 7% of the world's arable farmland. That ratio is brutal. Every acre matters enormously. Losing farmland is not an inconvenience. It is a direct threat to whether the country can feed itself without becoming completely dependent on imports. So when sand started eating fields at that speed, the response was not going to be a modest one. The first serious attempt started with trees. In 1978, China launched a program that would eventually be nicknamed the Great Green Wall. The idea was simple and looked good on paper. Plant an enormous belt of trees across the northern edge of the country, thousands of miles long, and use it as a physical barrier. The trees would slow the wind. Slower wind carries less sand. Less sand means the dunes stop advancing. Millions of people were mobilized. School children planted saplings. Soldiers planted saplings. Farmers were given quotas. Photographs from that era show endless lines of people walking into empty sand with buckets and shovels, and a lot of it failed. This is the part of the story that usually gets left out, but it matters, because the failure taught them everything. Planters used fast-growing poplar trees because poplars shoot up quickly and look impressive within a few years. The problem is that poplars drink enormous amounts of water. Planting millions of thirsty trees in a place with almost no rainfall meant the trees survived by pulling groundwater up from deep underground. For a while it worked. The strips looked green. Officials took photos. Then the water table dropped. And when the water table dropped far enough, the trees started dying, all at once, across huge areas. There are stretches of northern China where you can still see them. Thousands of dead gray trunks standing in sand like a graveyard. In some regions, the survival rate for planted trees was under 15%. There was a second problem. Planting a single species across a massive area creates what biologists call a monoculture. And monocultures are fragile. In the early 2000s, a beetle infestation swept through one of these poplar belts and killed roughly 1 billion trees. 1 billion. Decades of work gone in a couple of seasons because everything planted was identical and the beetles had an unlimited buffet. So by the early 2000s, China had spent enormous money and enormous labor and had a partial result at best. Some areas were genuinely stabilized. Others were worse off than before because now the groundwater was depleted too. That failure forced a rethink. And the rethink is where this story gets genuinely interesting. The new approach started with a very unglamorous observation. You cannot plant anything in sand that is moving. That is the whole problem. A seedling needs its roots to stay in one place long enough to establish. If the sand around it shifts every time the wind blows, the roots get exposed, the plant dries out, and it dies, or the sand piles up and buries it. So before you plant anything, you have to stop the sand from moving. The solution came out of that same railway line from 1959, the one that kept getting buried. Engineers working on it had tried everything: concrete barriers, fences, oil sprayed on the dunes to crust the surface. Nothing held. Then somebody tried straw. The method that came out of it is now used across millions of acres, and it is almost embarrassingly simple. Workers take bundles of rice or wheat straw, lay them on the sand in a line, and then jam the middle of the bundle down into the sand with a flat blade. The straw folds in half and stands upright, with maybe 8 inches sticking up above the surface. They do this in a grid pattern, roughly 1 meter by 1 meter, so from above, it looks like an enormous sheet of graph paper drawn across the desert. Those little straw walls do something remarkable. Wind blowing across flat sand accelerates and picks up grains. But wind hitting a grid of small barriers gets broken into thousands of tiny swirls that lose energy almost immediately. The sand inside each square barely moves. Within a season or two, the surface inside those squares starts to develop a thin crust of algae and bacteria and organic material. It stops being loose sand and starts being something closer to soil. It is also brutally hard work. There is no clever machine doing most of it. A worker walks into open desert carrying bundles of straw, lays a line, drives it down with a blade, steps back, and does it again, thousands of times a day, in temperatures that swing from freezing to blistering within a single shift. Crews have laid these grids across areas measured in hundreds of thousands of acres. Every square of that graph paper across the desert was made by a person bending over with a piece of metal in their hand. Only then do they plant. And they do not plant poplars. They plant low, tough, drought-adapted shrubs with root systems designed for exactly these conditions, plants that survive on whatever rain actually falls, without tapping the deep groundwater. The straw checkerboard method is cheap. It uses agricultural waste that farmers were burning anyway, and the straw itself decomposes into the sand over a few years and adds organic material. It works. That railway line that was unusable in 1959 has been running continuously for decades now, protected by a belt of straw grids and shrubs. But stabilizing sand is not the same as farming it. Stopping a dune from moving turns a disaster into a stalemate. It does not produce food. And this is where the story splits into a much more ambitious question, which is the one that actually shocked farmers. Can you turn sand itself into farmland? Not sand with soil trucked in on top of it. Not greenhouses sitting on the surface. Actual sand, converted into something that grows crops. For most of modern agricultural science, the answer was no. And there was a good reason for that answer. Soil is not just crushed rock. Soil is a substance with a specific physical behavior. When soil is wet, it holds together and clings to roots. When it dries, it becomes firm and supports the plant. It squeezes and releases as needed, holding water in pockets between particles and letting roots breathe. Scientists call this behavior by different names, but the practical version is this. Soil hugs a root, sand does not. Water poured onto sand runs straight through and disappears. Nutrients wash away with it. A root in sand has nothing to grip and nothing to drink. For decades, the assumption was that this gap could not be closed. Sand was sand. Then, a mechanical engineer at Chongqing Jiaotong University named Yi Zhijian started thinking about the problem from a completely different angle. He was not a soil scientist. He worked with materials and structures, and his question was not chemical, it was mechanical. He asked what physical property makes soil behave like soil, and whether that property could be added to sand artificially. His team spent years on it. They tested compound after compound. The idea was to find some kind of binding agent, a plant-based paste that when mixed into sand would give it that squeeze and release quality. Something that would let the sand hold water and hug roots like real soil without turning it into concrete. The story goes that colleagues were not exactly enthusiastic. Turning desert into farmland is the kind of claim that gets a scientist quietly filed under fantasy. Funding was hard. Progress was slow. Eventually they landed on a cellulose-based additive derived from plant material. Mixed into sand and hydrated, it changed how the grains behaved. The sand held together when wet. It held on to moisture instead of letting it drain away. And crucially, it did not lock up permanently. It kept that flexible, breathing quality that roots need. In 2016, they took it to Ulan Buh, one of the harshest deserts in Inner Mongolia, and treated a test plot of about 200 acres. Then they planted crops in it. Local farmers who saw the trucks and equipment arrive were, by most accounts, skeptical to the point of amusement. People had come to the desert with big ideas before. The desert usually won. The crops grew, not sparse, struggling, barely alive crops. Rice, corn, sorghum, tomatoes, sunflowers, watermelons. In some cases, the yields matched or exceeded what the same crops produced in ordinary farmland elsewhere in the region. And there was a second effect nobody fully predicted. Once vegetation established, the local microenvironment started to change. Insects appeared, frogs appeared, birds started showing up. In an area that had been effectively sterile, a small ecosystem began assembling itself. That 200-acre test expanded. Within a few years, it was thousands of acres, then spreading to other desert regions. Now, it is worth being honest about the skepticism, because there is plenty of it and some of it is fair. Critics have raised real questions. What happens to the additive over 10 or 20 years? Does the treated sand stay productive, or does it need repeated application? Where does the water come from, given that these are still deserts? Is this financially viable at continental scale, or only in showcase projects with heavy subsidy behind them? Those are legitimate questions, and the full answers will take decades to arrive. Anyone claiming this is a finished, solved technology is overselling it. But the fields exist. The harvests exist. Something that was considered impossible is now producing food, and that alone changed the conversation. And here is the thing. The paste method is only one of several approaches running at the same time, and some of the others are arguably even stranger. In the Kubuchi Desert, which sits in a bend of the Yellow River in Inner Mongolia, a company spent 30 years working on the same problem with a completely different toolkit. Kubuchi was, in the 1980s, one of the most hostile pieces of land in China. Roughly 7,000 square miles of sand. Locals called it the Sea of Death. There were no roads through it. A salt processing plant sat in the middle of it and had to truck its product out on a route that added hundreds of extra miles because there was no direct path. The company that ran that plant had a simple business reason to care. Every extra mile of transport was money burned, so they decided to build a road straight through the desert. Building a road through moving dunes is a nightmare. The first attempts got buried the same way the railway did in 1959, so they had to stabilize the sand on either side of the road before the road could survive, which meant planting, which meant water, which meant learning, painfully, over years, what actually grows in that environment. They landed heavily on a shrub called licorice. Licorice is remarkable for this purpose. It is a legume, which means it fixes nitrogen from the air and puts it into the ground, actively enriching the sand. Its root system spreads wide and holds sand in place. It is drought hardy, and it is a valuable medicinal crop that can be harvested and sold. That last part is the key to the whole thing. This was not charity planting. Licorice made money, so local farmers had a direct financial reason to plant it and keep it alive, rather than treating it as a government quota to be completed and forgotten. Tens of thousands of people ended up involved, planting licorice and other cash crops across the desert edge. The economics of that shift are worth sitting with for a second. A farmer planting a tree because a local official told him to has no reason to come back and check on it. A farmer planting licorice knows exactly what a kilogram of dried root sells for, knows roughly how many kilograms an acre yields, and will walk out at dawn to check whether the seedlings survived the night. Nobody had to be persuaded that the desert mattered. They only had to be shown that the desert could pay. They also worked out a planting technique that sounds almost too simple. Instead of digging holes by hand, which is slow and exhausting in sand, they used a pressurized water lance. You jab the lance into the sand, the water blasts a narrow hole about a meter deep. You drop the seedling in, and the wet sand collapses around it. What used to take several minutes per plant now takes about 10 seconds. One team could plant thousands of seedlings in a day. Survival rates jumped dramatically because the seedling went straight into moist sand at depth rather than dry surface sand. Over 3 decades, Kubuchi went from a dead zone to a landscape with roughly a third of its area covered in vegetation. Rainfall in the region measurably increased, which makes sense once you have plants transpiring moisture into the air. Sandstorm frequency dropped sharply. Farmers who had abandoned the area came back. And then they added something nobody expected: solar panels. Across enormous stretches of the Kubuchi, China built solar farms. Millions of panels laid out in rows across the sand. The obvious purpose is electricity, and these installations generate a lot of it. But the panels do something else. They shade the sand underneath. Shaded sand loses far less water to evaporation. The panels also break the wind at ground level, exactly like the straw grids do. And the panels need to be washed regularly to stay efficient, so there is a steady supply of water hitting the ground beneath them, which means the ground under a solar farm in the desert is dramatically more hospitable than the ground next to it. So they started farming it. Licorice grows in the shade between and beneath the panel rows. Sheep graze there. In some installations, sheep are used deliberately to keep vegetation from growing tall enough to shade the panels, which means the animals are doing maintenance work while also being livestock. One installation, shaped from the air like a giant horse, became something of a symbol of the whole project. But the shape is a gimmick. The actual innovation is stacking 3 uses onto one piece of dead land: power generation, sand stabilization, and agriculture, all at once, from the same infrastructure. Then there is Yinchuan, in Ningxia, where the approach went in a completely different direction again. Ningxia sits in a dry, sandy region with poor soil and limited fresh water. What it does have is enormous amounts of sunlight and huge quantities of underground water that is brackish, salty, useless for conventional farming, because salt kills most crops and poisons soil over time. So instead of fighting the salt, they used it. Ningxia developed large-scale saltwater aquaculture in the middle of the desert. Ponds dug into sandy ground, filled with the brackish groundwater, stocked with fish and shrimp species that tolerate or prefer saline conditions. The result is genuinely surreal. Shrimp farms surrounded by sand dunes, hundreds of miles from any ocean. And it works economically, because seafood commands a high price in inland China, and the transport advantage of producing it closer to inland markets is substantial. Even better, water drained from those ponds is nutrient-rich from fish waste. Some operations run that water through to irrigate salt-tolerant crops, getting a second harvest out of the same water before it is done. Ningxia also became one of the strangest wine regions on Earth. The area at the eastern foot of the Helan Mountains is sandy, gravelly, and drains well. Grapevines, unlike most crops, actually do better under a certain amount of stress. Poor soil and limited water forces the vine to push roots deep and concentrate sugars in the fruit. The region now produces wine that has won international competitions, grown on land that a few decades ago was considered agricultural waste. There is a harsher detail in the Ningxia story that deserves mentioning. Winters there are severe, and the vines cannot survive exposed. So every autumn, every single vine is buried under soil by hand, and every spring it is dug back out, across enormous vineyards. That is an extraordinary amount of manual labor repeated annually, and it is the actual cost of making that land productive. Now step back and look at what these approaches have in common, because there is a pattern. Every single one of them makes money. The tree planting programs of the 1970s and 80s were framed as environmental duty. Plant trees, stop sand, serve the country. And they underperformed badly, partly because of bad species choices, but partly because nobody had a personal stake in whether an individual sapling lived. The projects that worked attached a direct economic return to the ecological work. Licorice is a cash crop. Solar panels sell electricity. Shrimp sell at market. Wine sells at premium. Desert-grown melons and tomatoes sell into cities. The person doing the work gets paid by the result, not by the number of holes dug. That shift is probably the single most important lesson in this entire story, and it applies well beyond China. There is another pattern too, which is the willingness to accept ugly, slow, unglamorous solutions. Straw jammed into sand in a grid is not impressive technology. It is bundles of dead plant matter and a lot of people bending over in the heat. But it works better than the expensive concrete barriers did. So how big is all of this actually? China now reports that a majority of its desertified land that can realistically be treated has been brought under some form of control. Roughly 500,000 square kilometers of degraded land has been improved or stabilized. Forest coverage across the country has gone from single digits in the mid-20th century to over 20%. Sandstorm days in Beijing have dropped by a large margin compared to the peak years around 2000. And crucially, the direction has reversed. For decades, China was losing land every year. It now reports net gains. Land is coming back faster than it is being lost. Satellite data from independent sources has supported the broad picture. A widely cited NASA analysis found that a significant share of global greening detected from orbit over recent decades came from China and India, with China's contribution driven heavily by tree planting programs and intensified agriculture, which is not the same as saying everything is fine. There are real criticisms, and they should not be waved away. Some researchers argue that planting vegetation in dry regions depletes deep groundwater that took thousands of years to accumulate, which means the green landscape is being financed by a water debt that will eventually come due. Some argue that a percentage of reported success is measured by planting numbers rather than long-term survival numbers. Some point out that certain areas that were always naturally desert, and always had been for geological reasons, are being treated as if they were degraded farmland, when in fact, turning them green disrupts ecosystems adapted to aridity. The water question in particular is the one that keeps coming back. Vegetation that survives on rainfall is sustainable in principle. Vegetation that survives on ancient aquifer water is borrowing from a supply that does not refill on any human timescale. Distinguishing between the two across 500,000 square kilometers is genuinely difficult, and the honest answer is that in some regions nobody is entirely sure which category the greenery falls into yet. And there is a straightforward question of cost. These programs have consumed staggering amounts of money and labor. Whether the return justifies it depends heavily on how you count the value of food security, of clean air in major cities, and of villages that did not have to be abandoned. But the criticisms are mostly about degree and method, not about whether anything happened. Something clearly happened. You can see it from space. Here is what I find most striking about all of this. The core insight was not a piece of technology. It was a change in how the problem was defined. For most of history, desert was a category. A place was either desert or it was not, and you worked around it. The reframe was to treat desert as a set of specific, individual deficiencies that could each be addressed separately. The sand moves, so stop the movement. Water drains away, so change the physical structure of the grains. Sunlight is excessive, so shade it and sell the electricity. The water is salty, so farm something that likes salt. The soil is poor, so grow something that thrives on poor soil. None of those solutions transform the desert into a temperate plain. Each one just removes one specific obstacle and finds a use for what is left. And that is why farmers were stunned. Not because the sand became soil in some magical sense, but because the assumption they had held their entire lives, that this ground was finished and there was nothing to be done, turned out to be a description of the tools available at the time rather than a description of the ground itself. There are farmers in Inner Mongolia today who watch their parents' fields get swallowed by dunes and who now harvest crops out of ground that was under those same dunes. There are villages that were abandoned in the 1990s and repopulated in the 2010s. There are people whose grandparents left because there was nothing to grow and whose children are growing watermelons in the same place. The work is not finished, and it may never be. Deserts do not surrender permanently. Maintaining what has been reclaimed requires continuous effort, continuous water, and continuous money. Take the pressure off for a decade, and the wind starts winning again. But the assumption has broken. That is the real result. The idea that degraded land is permanently lost, that once sand takes a field, the field is gone forever, no longer holds. It has been demonstrated at a scale large enough that it cannot be dismissed as a laboratory curiosity. And that matters far outside China, because desertification is not a Chinese problem. It affects a huge share of the world's land surface, and it is accelerating in the Sahel, in Central Asia, in parts of the American Southwest, in Australia. Hundreds of millions of people live on land that is drying out under them. Whether the specific Chinese methods transfer cleanly to those places is an open question. Different soils, different climates, different water availability, different economies, different political capacity to mobilize labor on that scale. Straw checkerboards need straw, which means you need agriculture nearby producing it. Solar agriculture stacking needs enormous capital investment up front. But the general principle transfers perfectly well. Stop the surface from moving. Attach a cash crop to the ecological work so people have a reason to maintain it. Stack multiple uses onto the same land. Accept slow, ugly, labor-heavy methods if they outperform elegant, expensive ones. Match the crop to the actual conditions rather than fighting the conditions. Those are not Chinese ideas. They are just ideas, and China happened to test them at a scale nobody else has attempted. 60 years ago, a railway line in the Tanger Desert was being buried by sand faster than crews could dig it out, and the honest conclusion at the time was that the desert could not be beaten, it could only be endured. Today, that line runs through green, not because the desert gave up, but because a lot of people spent 6 decades failing, adjusting, failing again, and eventually finding the specific unglamorous methods that happen to work. That is usually how these things go. Not one breakthrough, a very long series of corrections. If you found this interesting, leave a like and subscribe. Every week, we break down the engineering projects, industrial systems, and large-scale transformations that reshape entire countries, and most of them get almost no coverage. Turn on notifications so you catch the next one. There are related videos on screen right now if you want to keep going. And here is the question I want to leave you with. If your country had land that was considered permanently useless, what would you try first, and would it be worth the cost? Let me know in the comments.